So if you could all come to equilibrium here. A question at the end of last day's lecture got me thinking. I was asked, is the collapse of bridges really due to resonance? And so I knew of this Seattle bridge. It's called the Tacoma Narrows Bridge, and but I really hadn't studied it or thought about it in detail, and so I started to do that. In fact, I wrote to a friend of mine in Cornell who had written about the failure of another bridge in about 2001, the so-called Millennium Bridge in London, which started swaying. And it seemed to be, and they are in fact resonance phenomena, but not in the way we really described in the context of the tuner, where we get a good response to an external signal. So let me talk a little bit about resonance today and various situations, because it really plays a very important role in many branches of physics. In fact, I put up a little poem. Does anybody know what the poem is called? I paraphrased. The time has come. No, it's not. It's close, but not. It's from, yes, it's from Lewis Carroll or Charles Dodgson. The time has come, the walrus said, to talk of many things, of shoes and seas and sealing wax, of cabbages and kings, and why the sea is boiling hot and whether pigs have wings. Well, I paraphrase this slightly. To talk of many things, of tuners, lasers, singing wires, of resonance and swings, and why Tacoma Narrows fell, and Millennium Bridge failings. Thank you. Let me first describe the resonance, just review the resonance that we talked about with respect to solutions of this second order equation with a periodic forcing, which we represent as a cosine or a sine, with a certain frequency omega, namely it repeats every 2 pi over omega seconds. We think of the R here, the resistance of the circuit, as small, so that the natural frequency of the circuit itself, if I forget this term, this is just d2q by dt squared plus 1 over LCQ. So the natural frequency then, it would be cosine of root 1 over root LCt and sine of root 1 over LC times t. They would be the natural oscillations of the circuit. And what we found is that the response was as follows. The response, there was a transient part, that's the decaying part, plus a part that didn't decay. It just oscillated, and it had the form V0 over omega times this factor, which we'll discuss now, cos omega t minus phi. And the current was a transient plus V naught over Z of omega, and then it was cos of omega t minus phi plus pi by 2. We got this by just differentiating this. Now this Z of omega is the sum of two terms, or at least it's the square root of the sum of two squares. One is this, and the other is the resistance or the damping in the circuit. The phase phi is just related to this, and the sine of phi is r over z of omega. So, the question is, a natural question is, when is the steady state, or it's an oscillatory steady state, it doesn't decay in time, it just oscillates in time, when is that the strongest? We'd like to know when you get a terrific response of the tuner. Well, to do that, if you want to get a good response, you want to make this factor, this z of omega, as small as possible. Because then 1 over z of omega is as big as possible. Now, what is z of omega? Well, it's the square root of the sum of the squares of the resistance and this factor here. So the failure of the circuit to respond strongly is principally due not to this guy, who is small, but to this guy. This guy is called the reactance. So it's kind of like an impediment to the response of the system. And it's called the impedance. So the impedance, okay, the effective lack of strong response, as it were, is mainly due to this guy being non-zero. But by a clever choice of omega, or in fact in the circuit what happens is this guy, you have a set of all sorts of omegas coming in on your antenna as an external signal, and you want to pick the particular omega you like, in other words, the frequency of your favorite radio station. And what you do, you have the power to tune by changing the capacitance of your tuner so that you can make this zero. In other words, you can choose the omega to be 1 over root LC. This is called resonance. Okay, you are a resonant response when the forcing frequency is the same as the natural frequency, root 1 over LC, of the undamped circuit. A similar situation arises if you're pushing a swing. If you're pushing a swing, let's see, what is the natural oscillation frequency? Well, if I divide ML here over here, and we approximate sine theta for small angle displacements as theta, the equation becomes d2 theta by dt squared plus g over L theta equals whatever the damping and the forcing. Here, the natural frequency is root g over L. In other words, if you solve this equation equals 0, the two solutions are cosine root g over Lt and sine root g over Lt. The period would be 2 pi over that frequency, 2 pi divided by root g over L, which is 2 pi root L over g. It's a formula you've probably learned for the pendulum a long time ago. Now, if you want to get a good response in this swing, if you're forcing it with a periodic forcing, it needn't exactly be cosine, it needn't exactly be up and down like that. It could be more, when we push a swing with a kid on it, it's more like we give an impulse every 2 pi over root g over L seconds. In other words, when the swing swings back here, we give it another little push, and then we don't do anything till he comes back again, give it another little push. But basically, if you analyze this in terms of cosines, it has a strong component of this cosine here. So now again, you'll get a strong response if the frequency you push at matches root G over L. In both these cases, the forces are externally applied. Here, the force, as it were, or the applied voltage, came from an electromagnetic signal traveling through the air, arriving at your antenna, and getting your tuner excited. Okay? In this situation, in the swing situation, we actually push every so often. So it's an external influence which makes the swing move. In a laser, roughly speaking, what happens is this. You have a gas or some medium, and its atoms have various degrees of excitation. Okay, they can be in higher energy level states or lower energy level states. And the key is, if the difference between the energy levels of two of these states, the natural frequency associated with that is you take the energy differences, divide by this Planck's constant, and that gives you a frequency. Now, if it should happen that you have an electromagnetic wave with frequency omega coming into this medium, what it will do is, if E2 minus E1 over H is the same as that frequency, it will excite the atom from the lower energy to the upper energy. And then it may fall down again and give out another photon. Now, a laser works because actually before you send in this signal at all, you hit the thing with very, very crude light, and you pump the whole thing so that all the atoms are up in this state. Then when this guy comes in, because there's this resonance, he triggers these guys to start dropping down. And the marvelous thing is, when these guys drop down and give off their photons, give off frequency omega, all the photons are phase locked. So you get a very strong coherent signal. So the laser works, you have to have prepared the medium into an amplified state. It has to be like an amplifier. There is a force. You do actually excite the thing with a certain frequency, but then it takes over because you've already got a source of energy there, and what you've done is just managed to tune it to the right frequency you want to get out. So in that case, in the laser case, it's really that you have prepared the medium. There is a natural frequency omega, which is connected with this energy level difference divided by H. And you just trigger this with an external force, and then you get this avalanche of coherent light out. So in that case, it's not really that all the forcing comes from this external source. This brings us to the case of the bridge, the Tacoma Narrows Bridge. It's very interesting. I started reading about it, and it turns out that originally people thought, well, yes, it's just this, that the wind comes along and there's fluctuations in the wind. You can think of the wind as being made up of lots of, you can think of the bridge as, actually it's a whole collection of springs. It has lots of modes of oscillation, but you could think of it in this as a paradigm here, where this is the air pressure fluctuations which are contained in the wind. Now, it turns out that certainly on the day that the bridge fell, the turbulence in the air did not, the spectrum did not match any natural frequency in this structure. There's lots of natural frequencies, by the way. A bridge is a complicated mechanical structure with it's like lots of linked oscillators together, and each of the oscillators have different frequencies. But the turbulence in the air didn't have any frequencies which really matched those frequencies that you found in the bridge. Then, actually, there was a commission appointed, and the lad who led it, very famous aeronautical scientist, a man called von Karman, Theodor von Karman, probably one of the most famous engineering scientists of his day. He was actually my academic great-grandfather. We academics have these family tree sort of funny things, you know, if your PhD supervisor, he's your father, and his supervisor is your grandfather, and so on. Anyway, von Karman was mine. And von Karman was actually asked in to give a report on the bridge and why it fell down. And they knew what the modes of oscillation, you know, there's wonderful pictures, you can look them up on YouTube, the mode actually that really got the bridge to come down was a torsional mode. Okay, so this is the span of the bridge, and the torsional mode is this one, okay? Only it was a mode where it twisted this way for half the span, and then twisted the other way for the other half of the span. So it was this sort of mode, and then tipping backwards and forwards, the whole deck of the bridge. So von Karman actually is very famous for a thing called the von Karman Vortex street. Has anybody ever heard of the von Karman Vortex street? Well, I'll bet you, yes, Ryan. Ryan is the guy who asked me this question. Do you want to tell everybody what the von Karman Vortex street is? Or?
A series of vortices swirling in opposite directions, alternating with each other.
Right.
And a fluid flows past the object.
Very good. Right. So we talked before about this, flow around an object. And if you have a flow around an object, unfortunately, what happens is you have stickiness because you have viscosity, and I explained to you before that the damping on this thing comes about because the flow separates. And when it separates, essentially creates vortices. Okay? And you get a whole stream of vortices coming off this. Okay? And downstream. And you see them coming behind this blunt body. And there's a certain frequency to them, because if you sit at a certain point, they'll pass you every so often, okay? Depending upon the wind speed and the diameter of the body. Roughly, it's a constant times the wind speed divided by the size of the body, the length of the body. Von Karman said, hey, this is the reason that the bridge fell down. You had a steady wind, and in fact on that day the wind was blowing at about 42 kilometers per hour, about that I think. What, 30 miles an hour or something? Anyway, it was blowing by, and these vortices come off, and that gives a periodic fluctuation in the pressure of the air. And that periodic fluctuation, it was like this as an external, it was like an external force here, and that would get the bridge going. One of the modes of the bridge would certainly respond to that. But the famous von Karman was incorrect, because later analysis and careful science showed that the von Karman frequency was nowhere near the frequency of the mode, this torsional mode, that actually brought the bridge down. Then several other people started working on this. And it's hard to know. There's lots of names. I have several papers. By the way, when I asked this friend of mine in Cornell, he immediately, because I pointed out that actually I thought it was very much akin to the explanation for the Millennium Bridge coming down, and he sent me back an email and says, I absolutely agree. I forwarded your thing to your idea to a friend of mine in Cambridge who had worked with me on this, and he has had similar ideas. And this morning, email is fantastic. I mean, in the old days, you'd be writing letters, and then you'd forget to put the stamp on, so they never got sent. But already back today came the response from Alan McRobbie in Cambridge, not only sort of agreeing, but saying, yes, and here's a paper we wrote to say that, and so on. So anyway, the idea, they're very clever. It's very clever. So I have some, if anybody's interested in the names, I forget the names now exactly who thought of these things. But here's the idea, though. You see, here's the deck of the bridge. Okay? The wind, say, is blowing this way. Okay? Now, what's going to happen is there are various modes of oscillation. One is the lift can change on both sides. The air is blowing over this. Okay? When this tilts, if this tilts a little bit like that, then it's like an aeroplane wing. There'll be more lift, more forces on the bottom. So the thing will want to go up and down. So certainly there's a possibility that this up and down mode can get excited. But there's also the possibility that this mode can get excited, the twist mode around the center. Around the center. And here's the interesting thing, what happens is the lift isn't crucial. It's actually the twist is the most important thing. So the mode, it's a twist mode, so you can think of it just like this equation here, where essentially this K over M is essentially the torsional, it's like the torsional Young's modulus. It's the resistance to twisting of this steel, this deck, okay, this particular bridge. Now, here's the thing, what happens. It's certainly you get a Karman vortex street from this is a fairly blunt, this isn't like a plate. This is a fairly blunt body, okay, because the bridge is fairly thick, okay. So you do get a Karman vortex street, all right, but the clever realization was that as this thing, it's in this mode of, supposing it starts very slightly to start twisting like this and this. Now you're looking end on. This is the way you drive across the bridge. And it's starting to go like this and this. You see, it becomes like an aerofoil, only it's like an aerofoil where the wing is oscillating up and down, like this, twisting. So when it's up here, there's an extra sort of vortex. When it gets up like this, there's the vortex that comes off the leading edge is a little bit different than the kind of vortex or the spin put on the fluid on the bottom. So what you have, and then of course when it goes into this position, it's the other way around. So what you have is that the bridge, that the motion, this motion itself causes a steady stream of air to shed vortices alternately on the top and then on the bottom, the top on the bottom, and this induces pressure fluctuations which actually increase, or can, in principle, increase the torque. Now, if the wind is blowing, so you can calculate, from the position of these vortices that just get that come off the tip just because it's moving up and down, it introduces, in fact, a pressure gradient which is naturally in phase with the frequency of the thing oscillating. because when it's up here, the less pressure here, and twists it back, and so on like this. So in fact, in this case, what happens is this force isn't like somebody pushing a swing. It's sort of induced by the interaction between the oscillation itself, in this case a twisting around some center line, and the pressure and the air. But the net effect is to produce something like that. Okay? But that frequency, the fact that that frequency matches root k over m, that's not just luck, because the external frequency, this doesn't come from some externally applied fluctuation, but it's a natural fluctuation which is the result of the alternate production of little vortices as the deck tilts backwards and forwards. So it very naturally has to be in tune. So it's as if it tunes itself. So in fact, what happens here is instead of that force, you get the following. You get a thing on the right-hand side, which I'll call C dx by dt. And then there's a little bit of k, no, not k, we'll call it dx. A little bit depends on the x, but mostly this. But now this becomes a positive amplification and not damping. So when this guy beats the natural damping, then the oscillation is just amplified instead of damped. It's effectively, it changes the damping from minus to plus because of this. Now, there's no mystery. The energy to drive this was in the wind. Okay? But the interaction of a steady wind with this oscillator produced a situation that you get a natural periodic response, which is in fact in tune, naturally in tune with the oscillators itself. And it's a resonance, but it's a resonance that was induced by the action or the oscillation of the deck itself as an airfoil. It has to be a blunt airfoil. If it was just a plate, if it was a very thin one, actually the C wouldn't be strong enough to overcome the B. So, so actually this is sort of written up. This is called flutter. And the aero means it has something to do with the wind, and the elastic is that this factor here is connected with the elastic properties, torsion properties of the bridge structure. Now, but von Karman Vortex Street, actually, to come back to that, that's the street. Now this is a time-dependent thing due to the wind, the tilt changing in the deck. You've all actually seen evidence or heard evidence of the von Karman Vortex Street. Do you know what Aeolian tones are? Has anybody ever heard Aeolian tones? Have you ever been out on a prairie and the wind is blowing and you hear the telephone wires singing? Yeah? Have you ever heard? Yeah. That's actually sound produced by the frequency associated with shedding vortices, the von Karman Vortex Street. So it's called singing wires or Aeolian tones. So they can come into play too, and they make music. In fact, in one of the things I was reading, apparently both Chopin and Beethoven included snatches of Aeolian tones in some of their compositions. So anyway, but now this, so now what's this got to do with the Millennium Bridge? Well, let me give you an example. Supposing we're on a ship at sea, and the ship is rolling, okay? It's pitching from side to side. And we've got hundreds of people on the deck. Now, when the thing tips this way, there's a tendency for everybody to all end up this side. And then when it tips back, we all go this side. So in fact, between us and this bridge, as it were, this ship, we actually enhance naturally, because we move left and right exactly with the natural frequency of the roll, right? You all fall over this side, and then you all fall over this side. And if enough of you do this, of course you can tip the ship, right? Absolutely. You just overcome the natural center of gravity and over you go. So actually people are asked, and in fact on aeroplanes, I remember once being asked on an airplane for people to spread out because the plane was going in a roll situation, and they were afraid at those years. I'm old enough, by the way, that you could stand up and stay in the back of an aeroplane, and you could actually drink there. You know, you didn't have to stay in your seat. I mean, modern day aircraft are terrible. On Ryanair, you know, they were talking about charging you to go to the toilet, for crying out loud. But anyway, what was I talking about? Rolls. So you can see this thing. Now, what happened on the Millennium Bridge? There was apparently about 30,000 people used it per day, or in the part of the day that people were up and about. And so there was, when the bridge was having these big wobbles, they noticed that there was about 2,000 people on the bridge at the time. And what was happening a little bit was this, is the bridge would swing one way, just people keeping their balance would step to, you know, just give an extra force just to stop falling over with the slight swing of the bridge. And then, of course, you'd swing back the other way. Now, if everybody did it at random, they didn't respond to the bridge, then there'd be no real net effect. But if everybody sort of started stepping in unison like this, and this is what happened, then it's exactly like this situation with the tilting airfoil. You're producing an effect which essentially resonates with the natural swing of the bridge. And so actually this is the paper that Steve Strogatz, the guy in Cornell, wrote, and it's in Nature from a couple of years ago. And so what they had to do, then of course, like I say, if I told you that what happens is the response, this driving becomes essentially a function of the oscillator itself. And what they had to do was up the B to beat the C. The C was always there, but they had to up the B. So they'd put in braces and struts, which severely damped this particular mode that the walking population would excite. So these are sort of self-induced or self-excited resonances. So you can see that you get very strong responses to systems when you are near this resonant point, okay? Now the difference is, like I want to emphasize, is sometimes there's an external influence carrying the particular frequency that's going to resonate with your internal frequency here, as in the case of when you tune your radio to get your favored station. But in these other cases, the bridges situation, or at least some bridge situations, you're in a situation where the motion itself just causes the air to act as if it's having a fluctuating pressure in such a way as to provide a moment, a torque, which is in tune with the natural frequency of the deck. Now, was there anything else I wanted to... Yes. So, any questions? Actually, it's a very... Yes?
You were saying that the torque on the bridge
opposite directions.
Right. Yeah.
So I understand how self-induced like resonance occurred.
Right.
How did that effect occur? Like, what was the pivot point?
Yeah, the pivot point, where there was zero torque, it was in the middle. Like it was that mode. It was the mode that I don't know, and it didn't seem to be addressed. Why that mode was preferred over the whole span, doing this and this.
Do you think that it would go like this, and there would kind of be a wave traveling through it?
You would, but it's the second mode. Yeah. No. So look, this is the wonderful thing, and thanks to Ryan for. It's always good to ask questions because it's amazing how people will tell you, "Oh, this is known," or "This is it," or "This is," when in fact a little digging shows you that this isn't the case. So your question, your first name again? Hunter. Hunter, yes. Hunter's question is, why did it choose this mode to go in? And I don't know the answer. Maybe the guys who wrote the papers, I haven't read the complete paper, were able to, yes?
I just believe that mode possibly set a different frequency than the mode of the whole bridge existing at once, sort of like the different harmonic modes.
That's true. That's right. But don't forget, these are self-induced. The fluctuations in the air kind of follow the natural frequency of the. But you may be right that the natural frequency of this torsion mode may not produce the pressure fluctuations. The effective C is probably not as big as in this mode for some reason that I don't understand at the moment. But this is something that you can work on. But nevertheless, the paradigm, the idea that you have natural oscillation, that you have an oscillator with very small damping, with a natural frequency, which is somehow forced either by its own interaction or directly forced from some external influence. This is a very important paradigm to keep in mind, not only just for springs and swings and tuners, but in many cases in chemistry and geology and lots of places. Very good. All right. Good. Now, we were a little bit ahead of ourselves, so I'm going to tell you about one more thing now, and then that'll be it for today. And next day, I'm going to start on a very dull thing compared to all this, but it's the method of variation of parameters for solving the kinds of equations we've been trying to solve. But I want to tell you about another phenomenon now. And it's connected with the notion of modulation. So it's called a beating phenomenon. Okay? It's very like the resonance. I have an oscillator which is described by this equation, and I force it with a frequency omega, and for the moment omega and omega 0 are going to be different, but not much different. Okay, and now I'm going to put on initial conditions, x of 0 and dx by dt of 0 is 0. Now you guys can solve this. It's like falling out of bed. You're so good now. So I'm not even going to go through the solution. I'm just going to tell you what it is. The displacement, the steady state solution is cos omega t divided by omega 0 squared minus omega squared. And the bit of the amount of the other solution, the solution of the homogeneous equation you have to add to satisfy the initial conditions, is just this. You can check. At t equals 0, x 0 is 0. And if you take the derivative, you get both signs, and that'll be 0 at 0. Okay. Now, you wouldn't know what that looks like. So I'm going to write it in such a way that we can try and understand what that signal looks like especially when omega 0 and omega are close. So what I'm going to do is this. I'm going to write omega 0 as omega 0 plus omega over 2 plus omega 0 minus omega over 2. And I'm going to write omega as omega 0 plus omega over 2 minus omega 0 minus omega over 2. That's fair. So I write it as the average and the difference. Now I'm going to use my cosine rule. You see, if I write cosine of omega t, this will be cosine of omega plus omega 0 plus omega 2 over 2 t minus omega 0 minus omega over 2t. Okay, so that's cos omega t, right? Now I'm just going to use the cosine rule. So I'll get cos one thing, cos the other, plus sine, sine. And I'm going to do that on both of these terms. And when I combine them, the sine, sine survive and the others don't. So I just get 2 over omega 0 squared minus omega squared times sine of omega 0 minus omega over 2t times sine of omega 0 plus omega over 2t. So you have a product. Now, you can see what's happening. If omega 0 and omega are very close, this guy is very small. In fact, the ratio of this over this, it has a nice limit. But the main thing is most of the oscillations come from here. Right? Because take omega naught to be 1 and omega to be 0.9. Then this is roughly sine t, and this is sine point t over 20. So this guy isn't going to change very much over a period of this guy. The period of this guy would be 2 pi over omega 0 plus omega over 2, or 4 pi over omega 0 plus omega. That period is much shorter than the period of this, what we call modulation. So what's happening is that if they matched perfectly, we'd get a resonance. In fact, in the limit, as omega 0 tends to omega, this becomes t over 2 omega 0 times sine of omega 0 t. So it starts oscillating bigger and bigger. It's a resonance. When you're a little bit away from the resonance, instead of getting it actually to grow like t, it'll grow like t at the beginning, but then, so initially, the two oscillators are in tune. But because the frequencies are slightly different, after a long while, the omega, this guy, will be actually trying to stop this moving. It'll be out of phase with it. And so you get a response like this. You get a strong resonant response. See, this is the underlying omega 0 plus omega over 2. You see the fast oscillation underneath? And then the slow modulation on top. So you can do this for yourselves. Use JODE. I use omega 0 as 1 and omega is 0.9. And you will get exactly this graph. Okay? So what's happening is you're getting reinforcement and then it's acting out of phase and so on. So in fact you can study, this is a phenomenon called beating. A beating of two oscillators. In other words, they reinforce and then they start cancelling each other. Reinforce, cancel, and so on. So, so this has the form here of a modulated, and we give these things names. We call this a carrier wave. This is the underlying carrier wave, and this is the modulation. And actually, when we want to put signals on things to send them electromagnetically, what we do is we have an underlying carrier wave, but then we beat, or we use some scheme to put this slow modulation on it. For instance, if you are listening to a radio station in AM, 600 kilohertz, and you're listening to some music on it, roughly the human voice is about 1,000 hertz. So we're talking about a difference from megahertz, say, to a kilohertz. The difference is 1,000. So the modulation, there'd be only significant up and down every 1,000 cycles of the underlying carrier wave. Okay, and then, so this is the modulation that sits on the signal, and what you have got to do when you amplify it with your tuner arrangement, pick the station you want, then you have to take off the underlying carrier wave. And that's what they do with diodes and things like that. So they just then end up just with the modulation. And then they have the modulation wiggle microphone diaphragm arrangement, and it recreates all the music, right? I mean, you don't think it's your voice that comes down a wire, do you? Comes down a tube all the way from whatever. No, you recreate with the diaphragm, you recreate in the air just with this modulation on the carrier wave. So these are words that you'll come across in many physical situations. Wave packets. How many people are doing physics here? Right, well, you know, we sort of think of, you know, there's this crazy quantum stuff which tries to get you to believe that an electron is a particle and a wave, and a photon really has particle properties. It's amazing. It's amazing. Hamilton knew about the particle behavior of waves. But that's for another story, I think. Yes, I don't want to get too chauvinistic here. It's now, where was I?
Quantum physics.
Quantum physics, right. In quantum physics, actually, we kind of model often particles as wave packets. Okay, so sort of wave packet, people think of it, and roughly speaking, well, let's just leave it there. So, but you'll come across this notion of a modulated carrier wave in your quantum courses as well. Very good. Well, now, there's only one more thing for today. And this is going to require you to be honest. I have a record of almost all the people who came to the various sessions, which got you credit for quiz number 7. But I don't have the record for the people last Monday who came between 10 and 12 in Math-254. Now, several of you came during that time, so I would like, we're going to stop early now today, I would like those people who came to the maths tutoring session last Monday between 10 and 12 to come down and sign again, please.